Good afternoon, everybody, and welcome to the Technology Seminar on the Ultra Large-Scale FFT Processing presented by enParallel Incorporated, and several speakers today. But first of all, Curtis Kent, who is CEO and President of enParallel, will give us an introduction. Curtis, welcome.
Thank you, Doug, and thank you everyone for attending. The presentation that Dr. Anderson will be giving in a moment was made possible because of the advances in supercomputing, particularly with the GPUs. We're seeing the supercomputer market changing from a closed architecture to more of an open architecture. And we feel that this has a tremendous impact for the users, the scientists, and the mathematicians of supercomputer users. Today, the users have to do things in a batch job. They have stuff they put in, they figure things out, but they don't get a chance to see their algorithms run from end to end. With our solution running on a desktop, they're able to actually watch it and observe and look for anomalies that may occur. The other area that this really impacts is the availability for the supercomputer across the wide spectrum. It's no longer going to be in a large room somewhere. It now can be in the scientist's office. And what I'm really promoting, as you'll see on one of the white papers, is putting the supercomputer out at the remote sensor, which I think is of particular interest for this group. Lastly, I think that's it. So what I'd like to do now is introduce James Anderson and bring him up, and then afterwards I'd like to talk some more about the usability of this technology with you. James.
Hello, everyone. It's a pleasure and an honor to be here. As Curtis mentioned, enParallel is all about leveraging the latest generation of GPU technology as vector processor heavy lifters. The applications that we work on are pretty much general purpose scientific computing, virtually anything that's appropriate to the vector processing model. Now, the main topic I'm going to talk about today is ultra large scale FFT, but actually that content is in the last 3 or 4 slides. And in order for me to effectively talk to you about this subject and to also, how should I say, validate our claims, I'm going to have to talk to you a bit about GPU architecture and also our processing model that we apply in order to get maximal efficiency out of these devices. So let's see how this works. So why ultra-large-scale FFT? Number one, FFT is a ubiquitous component in scientific and engineering signal processing applications, image processing applications. And in this context, when I talk about FFT, I'm talking about not only really big FFTs, but 1D, 2D, and 3D FFTs, full complex. Some of the applications: SIGINT, ELINT, ultra-wideband PHY, pseudospectral PDEs, for example, incompressible Navier-Stokes, something like that, denoising filters, high-speed convolvers, data compression, and so on and so forth. So our concept of the ultra-large-scale FFT includes 2 distinct scaling axes. Number one, size. What I'm going to show you is that we have a processing architecture that facilitates doing arbitrarily large FFTs. And then also speed. The GPU processing power is nothing short of incredible. You can, for example, you can purchase a commodity GPU device for about 50 or 60 bucks that has around 100 thread processors, an incredible amount of processing power, and also a very nice memory architecture, which I'll talk about, and very high-speed I/O. So why GPUs as FFT engines? Those of you who know about FFT, and I suspect that's everybody in this audience, would recognize a butterfly topology to the processing model, and but I'm actually speaking of GPUs for any sort of vector processing. And in this context, the GPUs are an outgrowth of the old SIMD, single instruction, multiple data concept for supercomputing that was developed some time ago. In this case, we're talking about a bank of thread processors, each of which has its own floating point engine and a very nice pipelined ALU, and also communicating with the other thread processors through a parallel cache, a very nice memory architecture, and I'll talk more about that in a moment. So that parallel cache consists of a number of components, a number of useful components: shared memory, by which a number of thread processors can talk to each other. There's also constant global cache, which all the thread processors can talk to, and then also a very high-speed texture cache. Now, this is something that is specific to the kind of graphics processing that you would find in the gaming world. But what it allows us to do within the context of scientific computing is to take advantage of spatio-temporal coherence in the data. And it's very high speed and very efficient, and I'll have more to say about that in a moment. Now, the overall memory model is hierarchical, and it's organized in terms of global memory at the CPU, device memory per GPU or vector engine, and then shared memory for a bank of the thread processors on the GPU. And for example, for the NVIDIA devices, this is described in terms of something called a warp, where 32 thread processors can talk to memory within a single clock. And then also a large register bank for each thread processor, which greatly facilitates pipelining of calculations through the ALUs associated with each of these thread processors. And this is a simple diagram of how the processing resources are organized on the GPU. So the device memory is global. Every thread processor can talk to device memory. Now, the bank of thread processors is organized in a sequence of multiprocessors. Each multiprocessor consists of multiple banks of thread processors. Within a bank, those thread processors can talk to constant cache, texture cache, and shared memory, and also have access to their own register bank. And notice here that you have a single instruction unit that is communicating with all of the thread processors. So this is truly single instruction, multiple thread processing. And just for a moment, I want to talk about some of the immediate advantages of GPU. And in particular, I'm comparing with FPGA. I come from an FPGA background, and FPGAs are incredibly sophisticated devices. And for specific scientific applications, even in high-performance computing, for example, as math coprocessor, reconfigurable math coprocessor engines, you can get very high throughput through these devices, but the development flow, the memory model, and a number of other aspects of FPGA are quite difficult, and also dealing with fixed point arithmetic. So a major advantage to be associated with GPUs is that they're programmable. And then also you get a very significant hardware abstraction at the application programming interface. For the NVIDIA devices we use, that interface is called CUDA. And for the ATI devices, I think it's called DPVM. I always get the V and the P mixed up. And then also you get significant parallel acceleration because, again, this bank of thread processors is operating in a cyclostatic pipeline, and they're all operating at the same time. And to the extent that you can get, if I can speak a bit colorfully here, to the extent that you can get every thread processor doing the same thing with no branches or checks or anything like that, you can get maximal efficiency out of these things.